Today I'll be talking about how I can identify the programmers or authors of binary executables. Oh, by the way, I have a question. Where is the remote? I'm not sure. How am I supposed to change the slides?
Is it this one?
No. How did she do it?
Right. Maybe can we get some help from the audiovisual team or the previous speaker?
Not this one.
It's this one.
To advance your slide?
Yes.
Yeah, green to advance.
Okay, thank you. Okay, back to the talk again. Okay, this is working now. And I have an army of co-authors. As you can see, this has been an intercontinental effort from Göttingen University in Germany, a startup, Sophos in the US, Drexel University, and Princeton University. I would like to thank all of my co-authors. Without them, this wouldn't be possible. At the end of this talk, we are going to see that style that's expressed in code can be quantified and characterized. And I will tell you how I started working on this project. In 2015, I published a paper about de-anonymizing programmers from their source code and introduced a principled and robust method to de-anonymize programmers. And after that, I kept getting the question, what about executable binaries then? And when we look at this executable binary, we see the source code sample on the left, and on the right, there's its executable binary version. I cannot really see much predictive or identifying information, but we can still work with this data. And why would I want to de-anonymize programmers from executable binaries? So first of all, I would like to know if we can still see coding style properties in compiled code. And if we are able to see coding style features or properties in compiled code, that would mean that we can de-anonymize programmers. For example, this can aid in copyright disputes, or it can be eventually used to de-anonymize malicious actors or malware authors. And we can also use this for verification. And these are security enhancing techniques, or it's a security enhancing technique. But unfortunately, there is no technical difference between security enhancing and privacy infringing. For example, we can think of oppressive regimes where they are trying to track the programmers of the country with that country's citizenship, and that might be privacy infringing if the government is trying to identify programmers of certain types of code. Let's look at this question from an interview by a security researcher. He is interviewing the Luabat malware author and asks, "Who are you?" And the answer is, just some guy who likes programming. I'm not known security researcher, programmer, or member of any hack group. So probably best answer for this would be nobody. So this nobody is what all the malicious actors want to be. They do not want to be recognized. They want to remain anonymous. But if we can de-anonymize them by their coding style, writing style, and so on, then they would be de-anonymizable, and they might be in trouble in that case. There has been a promising attempt at de-anonymizing programmers from executable binaries. And Rosenblum, years ago, he collected a data set from Google Code Jam, which is an annual competition. He compiled the code that he collected, and after that, disassembled the code and generated the control flow graph. And here we see a classic machine learning framework where we have training data, we extract features for certain classes, and after that, we test each file to find its programmer. And in this case, the machine learning model that's used is a support vector machine. I would like to compare Rosenblum's results to my results. First of all, we see that Rosenblum uses 8 to 16 files as training samples, and it's not clear how many he uses in each experiment. And for 20 programmers, he is able to de-anonymize them with 77% accuracy. Whereas in our approach, we're able to scale this to 600 programmers and use a random forest instead of a support vector machine, because random forests by nature are multi-class classifiers and they don't tend to overfit. And as a result, we are able to get 83% accuracy. So our lowest accuracy is higher than Rosenblum's. Our lowest accuracy is higher than Rosenblum's highest accuracy. So this is not just an incremental improvement. We are presenting a robust method for de-anonymizing programmers from executable binaries. And I would like to talk about the differences between Rosenblum's method and our method. We also collect data from Google Code Jam, which is an annual competition. Everyone is trying to implement a functionality for the same set of problems, and they have a limited time to implement the certain semantics for these problems. And if the solution is correct, it gets posted online. And as the programmers are advancing to higher rounds, the problems become more sophisticated so that we can also differentiate between more advanced programmers versus less advanced programmers. And this also gives us an advantage so that we can compare our results with Rosenblum's results. And once I have this data set, I compiled the source code samples, and I had more than 1,000 contestants, but not all of the code is compiling in this case, so I'm left with 600 programmers. I pre-processed the files, and this is the major difference that I have as opposed to Rosenblum's work, where I'm using various reverse engineering methods so that I can get a rich representation of the binary so that it can reflect coding style properties or just code properties. And for that, I disassemble the code. I also use Radar, which is an open source state-of-the-art disassembler to generate control flow graphs. I also use Hextrace to decompile the code and generate decompiled source code so that I can generate abstract syntax trees with a fuzzy AST parser called Yarn. And I'm especially saying fuzzy AST parser because even if the code is incomplete or wrong, this parser would still be able to generate the abstract syntax tree. And with this rich data representation, I extract the features and feed it into a random forest that's composed of 500 decision trees. And each of these trees split the nodes based on information gain criterion. And after that, each of the decision trees vote for a certain programmer, and the majority vote defines the de-anonymized programmer for anonymous binary executables. And in order to go to the details of the method, you can see the kind of data we are dealing with. I have binary executables. We cannot really understand anything from that cryptic data, but once it's disassembled, we get assembly code instructions, and then we further decompile the code so that we can get lexical features from the code, such as function names, variable names, and so on. And once the code is decompiled, we can also generate the abstract syntax trees as well as the control flow graphs. And I extract features from those sources for syntactic features and flow features as well. And after that, I perform attribute selection by information gain criterion as well as correlation-based feature selection, feed it into a random forest, which does not, again, tend to overfit, and then de-anonymize the programmers. For example, for assembly features, we can use assembly unigrams, bigrams, or 2 consecutive lines of assembly. Or for syntactic features, which are the structural features of the code, again, we can get AST node unigrams, bigrams, or AST depth. And for control flow graph features, similarly, we can get CFG or control flow graph, node unigrams, and bigrams. But once we get all of these features for 100 programmers and 900 binary executables, we get about 700,000 features. And this is not computationally efficient. And at the same time, there's a high chance that with 700,000 features, we will overfit. So I need to reduce the dimensionality and select attributes. And the first method I use is the information gain criterion, which reduces the features from 700,000 to about 2,000. And 2,000 is still not enough. These are the features that remain, that have low entropy at the end, so that, for example, the illustration on top, which is illustration A, shows how those features are pure. And once they are pure, they can differentiate between the programmers more accurately. Whereas if the information gain is low, then the purity, it would be impure, and that would look like illustration B, and it won't be very helpful. But yet, with 2,000 features, we can still not very well understand what kind of properties are still representing coding style. And in order to reduce the number more, I apply correlation-based feature selection. And in this case, I'm looking for features that have high inter-class correlation and low inter-class correlation, which is basically saying that for each programmer, there is a certain feature that looks very similar for that programmer's files, but they wouldn't look similar for other programmers. And we can see the illustration. For example, it looks like a cluster where we have green and blue dots. This can be the same feature, but there is the blue distribution for programmer A, and there's the green distribution for programmer B. And the interclass distance is high, so that they are not similar to each other, and they are good for differentiation. And then we are able to reduce the dimension to 53 features. Oops, how do I go back? Sorry. And with 53 features, we can analyze to see what kind of properties are making programmers de-anonymizable. And we see that from the assembly instructions, arithmetic, logic, or stack operations are quite identifying. And from the abstract syntax tree that has the structural features and properties, we can, for example, see file and stream operations, as well as variable initialization and declarations. And my first data set to develop this model used 100 programmers, and I have a distinct set of 100 programmers that I can use for validation. And once I take their 900 files and extract the features and perform 9-fold cross-validation, since each programmer has 9 files, I get 96% accuracy, which is showing that the method can generalize to other programmers. And I especially set 9-fold cross-validation because for each fold, there are 8 program files or 8 solutions to the same problems that the model trains on. And then there is the 9th problem, which is the same for all of the 100 programmers. And the classifier is trying to identify the programmer for this 9th problem. And with 9 folds, it's able to de-anonymize or identify the programmers of 900 executable binaries with 96% accuracy. And we see that with large-scale programmer de-anonymization, the accuracy degrades gracefully. With 600 programmers, the accuracy drops down to 83%. And we also wanted to see some real-world applications because in the previous examples that I showed you, we are using a very controlled environment so that we can control certain variables and develop our method. But in real-world scenarios, we don't really see such straightforward properties of binary executables. And for that, I wanted to look into optimized binaries or obfuscated binaries, as well as I wanted to look at binaries from GitHub and null.io, which is a leaked hacker forum, and some malware binaries. And I saw that with optimization and stripping symbols, the accuracy drops down to 72% from 96%. But in this case, for 100 programmers, the chance of correctly and randomly identifying a programmer is 1%. And here, when the accuracy drops down to 72%, this shows that stripping symbols or optimizations definitely do not anonymize programmers, so they can still be de-anonymized. And with obfuscation, I applied 3 types of obfuscations to the binary executable with OpenLLVM, which is open source. And the first one is inserting bogus control flow. Basically, I insert more control flow, make the code longer, but this control flow data is unreachable. And the second one is instruction substitution, where I substitute certain instructions with equivalent ones, but the code is going to look, or the instructions are going to look different. And in control flow flattening, the control flow graph's depth is, ends up being of depth 1. And these obfuscations reduce the accuracy from 96% to 88%, again showing that obfuscation, even obfuscations are not enough to anonymize these programmers. And with GitHub, I was able to get 50 programmers binary executables, and in de-anonymizing 50 programmers, the accuracy is 65%. And I will shortly talk about why it significantly drops to 65%. And in the second case, I'm looking at how we can de-anonymize 6 malicious actors. And I have 4 programmers from the null.io hacker forum and 2 basically malware authors. And in that case, we are able to de-anonymize these programmers with 100% accuracy. To take a closer look at the GitHub dataset, first of all, I collected data from 141 programmers. But as you might have experienced in the past, not all code on GitHub compiles. So at the end, I'm left with 50 programmers, and they have 200 to 344 files. And the accuracy in this case drops from 97 to 65. So if I were to use the controlled environment and Google Code Gem data, it would be 97%. But now we are looking at 65%, and there are multiple reasons for the decrease in accuracy. For example, some programmers had only 1 training sample or 2 programming samples in total. And when we don't have enough training data, the accuracy inevitably drops. And for example, some programs might be longer than others, which is also affecting the training data amount. And the more training data, the happier the machine learning classifier, because it can generate a better model. And these were some examples from real world or in the wild scenarios. And for future work, I would like to look at ways to anonymize programmers from source code or executable binaries, because once we know how to de-anonymize them, we can basically modify or manipulate those features so that we can anonymize the code. And I would also like to understand better how we can de-anonymize binaries of collaborative code, such as open source projects that are authored by multiple programmers. And eventually, the goal is to look at malware author attribution. And for that, to start the experiments, first of all, I need a data set. And if anyone has a data set of malware with known programmers, please get in touch with me, because this is the step that I'm in. Thanks for listening, and I would be happy to take questions now.
Good. We have time for a few questions. Ben?
Hi, Ben Zhao, University of Chicago. This is really interesting stuff. I like the original paper. I like this one too. Quick question. So when you did the training for the random forest, the input sample label data, were those samples the same programs, or are they completely disparate logic?
Oh, they were the same programs. All of them had the same semantics. So it trained on the same semantics and tested the same semantic, only to differentiate the authors or programmers by their coding style.
So I guess my question is, how complex does a program have to be in order to reveal something that is particularly stylistic about the coder? Right. So I could imagine if you were to give that task of writing "Hello World" to a set of 100 programmers, there's probably a very limited number of dimensions of where you can add, peculiarities of control flow and whatnot into a simplistic program. So how does the program complexity affect the absence or presence of style.
That's a very good point, because maybe using program complexity as a feature would also be helpful, but the less complex the program is, then it's harder to de-anonymize the programmers, because as you said, there aren't that many opportunities to reflect coding style then. But we have not analyzed that, but that's a good point, and it's another variable that we can control for and test.
Sure.
Tudor Dimitris, University of Maryland. Interesting work. I'm curious, so as far as I know, Joern works on C and C++ code. So do you need to know, when you analyze binaries, do you need to know what language they were originally written in?
Yes, that was one of the assumptions, because according to, for example, compiler identification and programming language identification, it's a solved problem in the literature, so we assume that we would know those, but that would require some extra step.
Can I ask another question?
Sure.
My second question is, so one problem with machine learning is that it's a black box, so it detects stuff, but you don't really know why. So I was wondering if, after doing the feature selection and when you actually were able to successfully de-anonymize some of these authors, if you looked at which features actually contributed to each de-anonymization.
Yes, we used 53 features for all of the experiments. So we use the same set of 53 features for all of them.
Right, but this contributes to the global performance. Right? So the different features may be relevant for different programs. That's why I'm asking if you know each detection, basically, what it was, if it was due to one feature or to multiple features.
I haven't looked at such fine-grained details on classification, but that's also a good point.
Maybe we can have the next speaker set up and maybe take only 2 very quick questions.
Yeah. I have a very quick question. How can you be sure in your training data set, the code is not copied from another guy?
That's a question that I get very frequently, and that's our assumption, that we believe in the ground truth, and we cannot know if it has been copied or authored by someone else, or if it's a product of some collaboration. So that's a limitation, basically.
Yes, because recently some paper says for the malware, lots of codes are often, copy, paste, or something like that. So if you just use your method and we cannot guarantee the ground truth is absolutely correct, do you think? I'm really confused about this part.
In such cases, we can try to perform verification or look at open world machine learning tasks to find confidence intervals so that we can understand if the code is a mixture of multiple authors. And there are multiple ways that we can approach such cases.
Yeah, the final question. Can I again ask the speaker to set up?
Hi, Bolin from UC Santa Barbara. So have you looked at adversarial attacks on such de-anonymization? Like how much effort, how much you need to change your code to evade being de-anonymized?
I haven't started working on anonymizing coding style, and I'm thinking about, for example, anonymizing writing style, and I know that it's not a trivial task, and you cannot completely automate it. It can be semi-automated. I'm guessing that it would be even harder to anonymize coding style.
Yeah, let's thank Alan once again.
Thank you.